Just making sure the presentation and the recording has started. I think it did. Great. Welcome, everyone. I'm Peter Kish from the University of Warwick. We're presenting our paper, Sublinear algorithms with 3.5+ epsilon approximate matching, which I co-authored with my supervisor, Sayan Bhattacharya, and Thatchaphol Saranurak from the University of Michigan. This work was partially done while I was visiting as an intern at the MPI. So what is the problem setting? We are working on the approximate maximum matching problem. The goal is to find a large matching of G, general graphs. No restriction to bipartite. Mu of G will stand for the maximum matching size of G throughout the presentation. And we'll say that matching is alpha multiplicative and delta and additive approximate mu of G is thus equal then size of m times alpha plus delta m. And we'll just say that it's multiplicative alpha approximate if there's no additive slack. So this would be a 3/2 approximate matching. So we are working in a sublinear model. What does that mean? Simply means that we're working in polynomially sublinear time in the size of the input. Goal is simply to estimate mu of G, not to actually find a matching. And a matching size estimate is defined to be alpha and alpha delta and approximate in the same way. So we work in the sublinear time. This means that we don't actually have time to order the input in a convenient format, so it does matter how do we access it. So the two models of access we will be considering are adjacency list access, where we can query the ith neighbor of a vertex in each step. And the other model we'll consider is adjacency matrix access, where we can query pairs of vertices and find out if there's an edge between them. So what are the limitations of this model? One cannot return a constant approximate matching in sublinear time, an actual matching. This is why we are referring to just matching size estimates, and this is standard throughout literature. Also note that if we are working in the adjacency matrix access model, additive slack is necessary. Just consider an empty graph and a graph with a single edge. With adjacency matrix access, you have to query almost every edges to find out that that edge is actually part of the graph. So the assumptions you can make throughout the presentation: mu of G, maximum matching size, will just assume it's large, say constant times n. The graph is just assume it to be dense for simplicity, and just think of adjacency list access throughout, but it will not be very important. So what are the existing results? There are a bunch of results for small max degree graphs, beautiful combinatorial papers, and there are some other results I can't quite mention here, but the two results we will talk, which are most relevant to us and very recent, are a beautiful Fox 21 paper, which showed that one can get a 2 approximation in maximum matching size in O tilde n time. And I think Soda 22, there was a paper which showed that if you are willing to go slightly bit above n, you can get slightly bit below 2 approximate, so you can beat 2 approximation. And the very same paper at Soda asked the question of how close can we approximate mu of G in actually sublinear time. And we take a big step towards answering this question. Our results are the following. We get a 3/2 epsilon approximate matching in n to the delta times 1 minus some function of epsilon time if we have adjacency list access. So this is slightly sublinear if the graph is kind of uniform, so they're not particularly large vertices laying out. We get 3/2 and epsilon an approximation in n times average degree to the 1 minus function of epsilon time. So this is always sublinear for any graph, and however it does have additive slack. And we get 3/2 and the same approximation ratio with additive slack in sub n squared time in adjacency matrix access. Note that in the adjacency matrix, where the whole input is actually of size n squared. So this is what one can consider to be sublinear. Even though the matrix itself might contain a lot of zeros, like non-edges, it is still size n squared. Do note that this theta epsilon factor is hiding a poly epsilon there. That's something like epsilon squared. So where does this fit in this picture? And puts a result there. So we consider this to be a significant leap. Do note that at this here at STOC, there's an independent and concurrently Okay, sorry, BPT 23 should be the number. There should be independently concurrently from us. There's a result for which is restricted to bipartite graphs, but beats 3.5 approximation with similar running time. And since the publication of this paper, we have actually published a result which gets down to all the way to 1+ε in the adjacency matrix access model, not for list access. However, the epsilon term in the 2 minus f epsilon is actually way, way smaller. So what are our tools? Locally computable algorithms and EDCS. These were the two big steps. So let's talk about locally computable algorithms first. As the name entails, these are algorithms which only compute the output locally. Hence, they can be actually very much sublinear in the total size of the input, as they don't have to calculate the whole output. In this context, imagine locally computable matching algorithm to be for some alpha approximate matching. You fix a vertex, and it will tell us in very efficiently whether that vertex is matched under this particular matching. So say if this would be the matching and one query is V, then it should just return us the edge VU or just the match status is V, depending on how they define it. One important notion here is that queries in parallel return a consistent answer. So if we were to query V and we were to query U, they should point at each other. Otherwise, this doesn't quite make sense. And why is this useful for us? So this is quite standard so locally computable matching algorithms are quite standard tools to obtain sublinear algorithms. There's a simple recipe to convert them. Given an alpha approximate matching LCA, we just query the match status just as some random set, depending on the application, as can be polylog n or delta size. And we just extrapolate the ratio of matched vertices in S to the whole graph. We just consider it to be an estimator. So something like this. Say S is, as on the picture, queried vertex set. We observe that almost all of them are matched. So mu of G has to be something like n over 2. Obviously, this just adds some additive or multiplicative slight depending on the size of S. There are just details in the paper about this. So which matching LCA will we be using? We'll be using a beautiful result from 2012, Yoshida, Yamato, sorry, I don't recall the third person, apologies. It's a wonderful paper which shows that one can get a 1+ε approximate matching LCA in delta to the 1 over epsilon squared time with adjacency list queries and n times delta to the 1 over epsilon squared time with adjacency matrix access. So this makes sense for small degree graphs, of course. Do note that, sorry, the second one is, so do note that with n adjacency matrix access, we can execute a single adjacency list access because we can just iterate through the neighbors of a specific vertex. So this is where the connection is coming from. The other component is EDCS, which stands for Edge Degree Constraint Subgraph, and this was introduced by Bernstein and Sayan as 2015 paper, I think, on ICAL. So an EDCS is a sparse subgraph of the graph, which is guaranteed to contain a 3.5 epsilon approximate matching. So this is what we refer to as a matching sparsifier. So what is the definition? So a EDCS H is a subset of the edges with two parameters beta epsilon, which you can assume to be some constant. There are two properties. Property 1 says that any edge inside of the EDCS should have maximum edge degree beta. By edge degree, we will refer to the sum of the degrees of the two endpoints. So say that edge has edge degree 3, because this is a 3 1/3 EDCS. And the other property is that any edge outside of the EDCS should have edge degree greater or equal than beta times 1 minus epsilon. So not 1+ε, 1 minus epsilon. Apologies for that. So in this context, that would be 2, and see that black edge has edge degree at least 2. So property 1 ensures sparsity, since the max degree is beta. There can be beta many edges, and beta here is a constant. And property 2 on a high level ensures that edges which don't actually appear in H are just well represented by H because they have a lot of neighbors in H. I mean, this is a high level explanation. It's a very counterintuitive machine. So there are some very well-established properties of EDCS in nature, namely that it contains a 3.5+ε approximate matching of the graph. And this is the main property we will be using here. But in fact, something more general is true, and this was observed by Bernstein 2020, that let's just dissect the graph's edges to two sets, E of H and U, where H is an EDCS of E of H, but it is not necessarily an EDCS of U. In fact, vertices of U has lesser than beta times 1 minus H degree. We call the edges of U. We will call these edges underfold edges, something like on the picture. On the right, all of those edges have 0 edge degree in H, where H stands for the red edges. And it's also true that H union U contains a 3.5 plus epsilon approximate matching. We'll not prove this here. It's proven in Bernstein 2020. It's a very useful property of the EDCS. So how do we actually construct an EDCS in a sublinear world? This is building on a standard algorithm from Bernstein and Stein papers, but we implemented in the sublinear model. So we just initially set the EDCS to be empty, and we repeat the following simple operation. This is a standard greedy algorithm. So if we find an underfold edge, that is an edge which has a small edge degree outside of the EDCS, that edge should be included in the EDCS. Otherwise, because the definition there is violated, so we just add it to the EDCS, something like that. And if we find an overfold edge inside of the EDCS, which has edge degree which is greater than beta and should be thrown out because it's too large, we actually just throw it out. So something on the middle edge there has edge degree 4. We want it to be 3. We remove it. And this greedy process can be repeated arbitrarily. And Bernstein and Stein, the very same people which introduced this concept, showed that there can be a bad O tilde n underfold edge insertions and overfold edge deletions. So these update steps on any EDCS, on any graph. So this process compiles, and it actually compiles in time proportional to n. So let's just remember this property. This will be very useful later. Do note that if there's no underfold edge outside of the EDCS and there's no overfold edge in the EDCS, that means that property 1 and 2 of the EDCS is satisfied. So H is actually an EDCS of G. So this is when the construction is intuitive. So how does our sublinear algorithm look like? It is based on the streaming algorithm from Bernstein 2020. And it has 2 phases. In phase 1, we construct H, a sort of EDCS, not exactly an EDCS. So we will repeat the following process. We sample the sublinear number of edges in N from just randomly from the H set. And if there is an underfold edge inside of S that should be part of the EDCS, we add it to the EDCS, and we remove overfold edges, which this addition may cause. If in S we don't find a single underfold edge, we just compile and proceed to phase 2. Simple as that. So we just take random samples, greedily try to extend our EDCS. If we extend the EDCS, we restore its properties through removing overfold edges. And if there's no underfold edge in our sample, we just stop the phase. So keeping this algorithm in mind, let's just try to analyze what guarantees we have based on the earlier properties. Since there can be at most O tilde n underfold edge insertions and overfold edge removals with the EDCS, we will revisit case 1 at most O tilde n times, which means that the total time of this operation is O tilde n to the 2 minus delta. Removing overfold edges can be done efficiently, not that here. And also note that when phase 2 started, S had no underfold edges. So we can with high probability make an argument that there are very few underfold edges in the whole S set, something like M over size of S, which is going to come to n to the 1 plus delta, assuming that the graph is fairly dense. And if we drop large degree vertices, we can also assume, say, that it is not just that the set of underfold edges are sparse, but they also have a small maximum degree. Let's refer to them as U, and let's assume now that we get the high probability guarantee that their maximum degree is n to the delta. Then in phase 2, we will use Yoshida's LCA to find a large epsilon, to construct an LCA in this H union U data structure. So U stands for the underfold edges of H with respect of E with respect to H. And recall earlier that we have mentioned that there's a useful property of the EDCS that H union U in this context is guaranteed to contain a 3.5 plus epsilon approximate matching. And also recall that by construction, we assume that U has maximum degree n to the delta. And since delta here can be set to be an arbitrary small constant, the LC algorithm can actually efficiently query this structure H union U. So max degree of U is n to the delta, but we don't actually have access to delta. But do note that H is explicitly calculated, and whether an edge is in U or not really just depends on the edge degree in H. So if we query an edge of the H set, we can decide whether it's in U or not. So we have adjacency matrix access to U. All in all, this guarantees that Yoshida's LCA runs in slightly superlinear time. That is the term on the right, so n to the 1 plus delta over epsilon square. And the first phase also took some time, n to the 2 minus delta to complete. That's kind of a pre-processing step to find H. But putting it together, we just need to select delta. So this expression on the right is sublinear, which is actually quite simple. Delta just needs to be something like epsilon square. And we generated the 3 alpha steps in approximate matching LCA with some pre-processing time. And if you recall the reduction I mentioned earlier from LCAs to sublinear algorithms, where you just sample some small set and test matching sizings of them, this implies that we actually get something like a 3 alpha steps in approximate sublinear algorithm. So this very simple logic is behind all three of our algorithms. Obviously, I'm scheming through a lot of details here. So what are the main takeaways I would like you to have after this talk? We can significantly beat to approximation in sublinear model. So we answered the question asked at the 2022 paper. And also, matching specification is possible in the sublinear model, surprisingly, even though we have access to very, very few edges of the graph. What the open questions I would propose is so these three sublinear algorithms which were on that chart, which work in the 3-half and lesser regime, they all work in almost n squared time. It would be interesting to see if there is something which is closer to n or tilde n, which is actually necessary in this model for anything to work. And also possible extensions like weighted matching, B matching, sublinear set cover. So any sublinear LCAs and algorithms for these problems would be very interesting in my opinion. Thank you for watching.